No Austin. No Sally. Okay, thank you. That is why I say this, so people can correct me. And there's Jaron and no Jerry. No, he's not. I have you marked here, Jerry, just in case you think I'm actually... Okay, we're going to talk about some eddy currents and inductors. That picture is a special kind of inductor called a mutual inductor, otherwise known as a transformer, which is clearly more than meets the eye. But before we start talking about new material, I have 2 clicker questions. And give me a sec. Okay, it is open for answering now. So the first one, what will not produce a magnetic field? Sally Toussaint.
I have to change my channel.
Not just Sally. Okay. We had 2, 6, 9. Now, what will not produce a magnetic field? A magnetic field, we learned that, first of all, having a magnetic dipole creates a magnetic field, right? We have all those little grains in a metal that creates a magnetic field. That was not one of the things listed here, but that was the first thing we learned that makes a magnetic field. Then we learned that if we have a wire with a current through it, that will create a magnetic field. Or if we make a coil of wires with a current through it, that of course will also create a magnetic field. None of those were asked here. This was specifically dealing with what's going on with Lenz's Law. So with Lenz's Law, we're talking about if I have a coil of wire, well, truthfully, I should be a little more specific and say anything that creates a current is going to have to create a magnetic field. So we should probably just back up there. Anything that creates a current will make a magnetic field. Does changing the magnetic flux through a stationary coil induce a current in the coil? If I have a changing magnetic flux in a stationary coil, will it induce a current? The answer is yes. And in fact, we had Faraday's law of induction. The E induced is equal to minus N change in magnetic flux over change in time. So it's going to produce an EMF, which means it'll produce a current. And if it produces a current, then it's going to produce a magnetic field. So this one makes a magnetic field. Next one, moving a wire through a constant magnetic field. If I have a wire like this and I move it through a magnetic field, what is that going to do initially? When I start moving, what's going to happen? Say louder, Ann. Okay, when I start moving, it's going to create a current. If I move at a constant speed, then it will reach a constant voltage difference and no current. But if I'm changing the speed, then it would still do it. So as long as I change the speed, actually I'm going to put changing velocity. If I'm changing velocity, then it will create a current and a B field. Now the last one, moving a coil through a constant magnetic field. If I move a coil through a constant magnetic field, anything that I try to make in one direction, I'm going to try to make in the other direction. And so it's going to have a net result of 0. Unless there's an option here that I didn't specify, so you could have said, well, I was thinking this. If it's rotating rather than just translating. If it's rotating, then it will create a magnetic field. When I wrote the question, I was only thinking translating, so the correct answer was supposed to be B. But if you were thinking rotating, well then C would be a correct answer as well. Okay, second clicker question. What is Lenz's law? You can answer now. Don't need to calculate, Sally. Just put an answer in. Okay. Everybody's answered 73403. Now, we don't have the correct answer well represented. Let's look through each one of these. Starting at the top, a changing magnetic flux induces an EMF. True or untrue? It's true. But that's not Lenz's law. Whose law is that? That's Faraday's law. A changing current induces a magnetic field. True or false? It's true. I didn't need this changing here at all. So I'm going to combine these two. A current creates a magnetic field. That's a true statement. Anybody remember whose law that is? Yep. So Ampere's law says that a current creates a magnetic field. Going down to D, a changing current induces an electric field. We haven't studied it yet. This is actually an addition to Ampere's. We'll learn more about how that plays in. That's the one thing Maxwell adds to Ampere's law. Actually, no, I got to think about this. I didn't think about this clearly. A changing current induces, an electric field induces a current, not the other way around, I think is what I should have done there. The last one, an induced EMF acts to oppose the change in magnetic flux. Oh, that is the one we like to call Lenz's law. Now, I don't know if it's the next slide, but I have a couple pictures from the textbook to help explain that. Yeah, so first, there's supposed to be a list of like 5 things there. Oh, wait, no, that was supposed to be the picture. Well, sorry, we'll just go to this list. If the picture is not replicated again, then I'll talk about it especially. So what we've learned this semester, we first learned about a force between charges, something that had long been recognized and studied, and it was Ben Franklin, great American scientist, and diplomat, went to France, and founder of religions. He did many, many things. He was the one who arbitrarily said that whatever the charge is on the amber rod, we'll call negative. and amber in Greek was electron. And so the electron is what was on the amber rod, so electrons have a negative charge. And we have from that our basic Coulomb's law, from which we have positives, or not positives, likes repel and opposites attract. And Coulomb's law tells us the strength of that force. Then we learned about electric fields. And the whole point of electric fields was to make it easier to calculate forces. So we defined, for instance, electric fields were equal to the Coulombic force divided by charge. And then we could use that definition to work the other way and say, so now I have an electric field here. What's the force going to be on any old charge? Then we started learning about magnetism. So our first test came just after that. But then we started learning about magnetism, and there are two types of magnetic charge. And they didn't want to call them plus and minus again. And they noticed that one of them was north-seeking, that is, it would rotate so this same side pointed to the Earth's North Pole, and so they called that north. And of course, what devastating outcome did that have? Yes. Since opposites attract, the north-seeking pole seeks a south magnetic pole, so the North Pole is a south magnetic pole. And we have never, and we will never, deal with the force between two magnets. That is, we won't have an equation to talk about the force between two magnets. Just that, as with electric charge, magnetic charges, opposites repel, likes attract. I said that backward. Opposites attract, likes repel. But we did have an equation for the force on moving electric charges in a magnetic field. So we have this equation. I don't know any name for it. Force is equal to Q V cross B, or is equal to I L cross B. They mean the same thing. Moving charge in a magnetic field will have a force. And remember that cross product is important because it gives both direction and magnitude information. And so you have to have the right hand rule going for determining the direction of the force on a charge moving in a magnetic field. Then we have moving charge creates a magnetic field. That is, if I have a wire with current through it, it creates a magnetic field. And so we have Ampere's law, and for people in Physics 252, the Biot-Savart law. Those are two different laws that are really fundamentally the same, that allow us to, just like Gauss's law and Coulomb's law are fundamentally the same, if you study them enough. They allow us to determine what the magnetic field will be produced by moving charge. And finally, the last thing we've learned is that changing magnetic flux creates an electric field. And we had Faraday's law and Lenz's law that worked together, hand in hand, to help us understand that. So this is just a quick, make sure we understand where we are, how we've gotten here, because each step really built on the next. And one of the important things to realize is the tight interaction between electricity and magnetism. One of the things that in higher physics you learn is that magnetism is really, it can be treated as relativistic electricity. And so you can solve all your problems just using electricity and relativity equations, or just using magnetism and relativity equations. We don't do that because it's hard. Instead, we do it the way it was first learned. But there's our background for where we are now. I don't have the picture that was supposed to be here. So what this was supposed to be was a picture from your textbook that shows a coil with wires going to a galvanometer, and then you have a magnet north-south, and the magnet is being pushed into the loop. So obviously my picture is not the perfect picture here, but imagine that magnet is being pushed up into the center of the loop. Now, what direction are the magnetic field lines from North Pole? Do they go into the North Pole or out of the North Pole? Out of the North Pole. So my magnetic field lines are coming up Oh, let's see if I can be real tricky. It's probably not going to happen, but right, the magnetic field lines are going like this. Now, if it is moving in, what is happening to the magnetic flux? It's increasing because the strength of the magnetic field lines, just like with electric field lines, the separation between them tells you the relative strength. So as you move that in, the relative strength is getting stronger, so the magnetic flux, which is B dot A, is increasing. So then we look from that to Lenz's law. That's a Z. That's an S. Induced current will oppose change in flux. So the magnetic field is pointing up and the flux is increasing. So to keep the flux constant, what kind of magnetic field do you need to add? Magnetic field is up and getting stronger. To keep the magnetic flux constant, what do you need to add to the magnetic field? Something that's pointing down. So the B induced must oppose the B, I'll say external, the magnetic field that's coming from whatever's making my magnetic field. And so if that's Lenz's law. Right there, the black. So if I have an induced magnetic field that's pointing down, if I have a coil of wires, how do I determine the direction the current is going to make a magnetic field that points down? Right hand rule. I take my right hand and I wrap my fingers in the direction of the current. My thumb points the direction of the magnetic field in the center of my coil. So if I want the magnetic field in the center to point down, then my fingers are going to have to wrap like that. And so the current is going to be going that direction. So Lenz's law told me the direction of the current. Or if I had something that was a little more sophisticated, like over here, I have a resistor, it telling me, aha. So the current is going like this, so that means that the voltage is like that, and I can determine the direction of the voltage that it's induced. So Lenz's law tells you the direction of the current or the direction of the induced voltage. And what law tells us how big the voltage induced is? Faraday's law. So I have to combine Lenz's law with Faraday's law. That is a very nice YS combination. That says the induced voltage is equal to, this minus sign is only to remind me that I need to use Lenz's law to get the direction. And change in magnetic flux over change in time. So depending on how quickly that flux is changing, my induced EMF will be bigger or smaller. So those work together. So that's what that review was supposed to be. It had like 3 more pictures, but I won't try to draw more pictures there. Instead, we'll get straight to eddy currents. So if we look at these pictures, I have a magnetic field. Based on the pictures alone, you have a circle with an X in them. What direction is the magnetic field pointing? Into the stream. So that, you see up in the top left, it does say V in, but you can tell from the X's you didn't need that. So I have a magnetic field that's going into the screen, and then I have this little piece of metal that's swinging in and out of the magnetic field. When it's swinging into the magnetic field, there is a change in flux. It's going from 0 to having the magnetic field pointing into the screen. And what direction is it going to induce a current if you're going from 0 to having a magnetic field into the screen? Okay, it's going to have to make a magnetic field out, which means it's going to have to go counterclockwise. Now you notice that picture shows clockwise. Why does it show clockwise? Because the velocity is the opposite direction of what I just described. If it's going out, then the magnetic flux is decreasing, and Lenz's law says, well, then I need to induce a magnetic field the same direction to keep it constant. And so it's going the opposite direction. If your magnetic flux is increasing, it's going to oppose the magnetic flux. If it's decreasing, it's going to be in the same direction. Now, work energy. We have current that's created in this conductor. Electrons that are going around in circles. They were originally not doing that. You had to do some work to make them do that. So energy had to be put in. Now, as these electrons go around in circles, there's resistance in the material, and so it takes energy to keep them going. Where's that energy going to come from? From the motion of the swing. So what's it going to do to the speed of the swing? It's going to have to slow it down because it's going to convert the kinetic energy into the energy of the charge moving and then dissipate. So we call this effect an eddy current. Why an eddy? Because an eddy is a small little loop like this. So they're eddy currents because they're little loops. Now this is only going to occur if it's in a conductor, right? If you have an insulator, you're not going to have the charge make an eddy current, so you're not going to have this interaction. But it makes cool effects. Now notice the picture on the right. What's different fundamentally, the picture on the left to the picture on the right? On the right, you have little strips, which means that you can only make little tiny eddies. And for making those little tiny eddies, there's going to be less energy involved, and so you're going to have less of an effect. Whereas if you have a big plate, you can make big loops and have a much bigger effect. Now I want to demonstrate, and I need somebody to come help me. Okay, thank you. Okay, this here is a brass tube. It's non-magnetic. No interaction here. Obviously, at least one of these is a magnet because they're sticking together. We'll check to see. That's a magnet. This one's not. Okay, I'll let go just so you can see. Yep, not. So we have not a magnet. Now what we're going to do is, I will have, do you want to hold this or drop this? Okay. Now what she has to do is she has to try to hold it so it's just hanging straight down. It's very hard to do it right. And I have to drop it so it just goes through the center. That's also very hard to do right. So if you hear a hum as this hits the sides of the wall, that just means that we messed up. So we'll do it until we get it right. So I'm going to drop it. See, that was wrong, right? You heard it? So no, don't hold the bottom. If you hold the bottom, then it's not going to be vertical for sure. Part of it is my drop. Okay, that went quicker, but you still heard it on the side. Okay, that was horrible. I'm going to try one more. I think you know the picture. It basically drops inside, just like it would like that. Now we take the magnet and we do the same thing. You got it? So drop the magnet. Notice it's not hitting the side, but it takes a really long time to come out. Why? That's all. Very simple. Why did it take a long time for the magnet to go through instead of just dropping through? That is not how you drop it in there, folks. This is the non-magnet one, but I hit the sides. Okay. It's eddy currents. What you have with this tube, and of course I can draw pictures and talk till I'm blind. Talking doesn't make you blind now, does it? Horse. Close enough. So I have my tube like this. And inside that tube, I'm going to put a magnet. So let's put the magnet. There's the magnet. And of course, one side of the magnet is, let's say, north, and one side is south. Now, if I draw the magnetic field lines, how do I draw these magnetic field lines? They go out of where and into where? Out of north and south. So they're going to go like this. Now, if we look at the blue tube, what's happening to the flux in the blue tube below my magnet? Okay, the flux is increasing. And what direction is flux pointing here? The magnetic field inside, right at the bottom? According to these arrows I've drawn, what direction are they pointing? Up. So the B, the net magnetic field inside of my little tube was upward and increasing. Now, according to Lenz's law, if the flux is increasing, what's going to happen for induced currents? It'll create a magnetic field that is opposing if the flux is getting stronger. So I'm going to have, according to this, current to make an induced magnetic field that goes the opposite direction. So I have my magnet has south pointing down, and I have my induced magnetic field that is going to have south pointing up to oppose that induced magnetic field. What is actually making that induced magnetic field? It's going to be electrons that are going around the loop below it. But they're making a magnetic field that's opposing the magnet, and so it's going to slow the descent of the magnet. Now, according to Faraday's law of induction, the EMF and thus the strength of the induced magnetic field is proportional to the change in flux, and thus proportional to the speed. So the B induced is proportional to the speed. The faster it goes, the bigger that induced magnetic field, the stronger the repulsion, the more it slows down. Now, if I look at the top, I have just the opposite situation. At the top, the magnetic field was pointing up, but flux is doing what? Decreasing. So if flux is decreasing, what direction is the induced magnetic field going to have to point? If the flux is decreasing, it has to point the same direction to try to keep the magnetic field constant. And so my B induced is going like that. So what do I have on the top? I have a north facing the south. Is that attractive or repulsive? Attractive. So the top of my magnet is being pulled up by the eddy currents in the tube above it. The bottom is being pushed up by the eddies below it. So both of those are making upward forces, and so the net upward force is proportional to the velocity. The net downward force, of course, is proportional to gravity. And you will reach a fixed speed where it just falls at constant speed because the downward force equals the upward force. Before I go to the next I'll go to the next slide and then I'll do this. Spread out my... Oh. There was a picture here. I know I put them in there. Something went wrong with the save, apparently. There was a picture here showing how roller coasters use this effect. The picture is in your textbooks. You basically have, on the sides of roller coaster tracks, you'll have magnets like this that make a really strong magnetic field that goes like that. And then when the roller coaster comes by, the roller coaster will have a blade that goes through that. And when the blade goes through it, on one side of the blade, the magnetic flux is increasing, the other side is decreasing. You're going to have the same effect, making magnets that oppose that blade going through. And so it slows the roller coaster down. Even if there's no power, these will slow the roller coaster way down so that it can crash safely if there's no power and whatnot. Okay, so that didn't work out. Let's go to my demonstration. This here is the solenoid. What does the solenoid mean? A bunch of coils. So I have a bunch of coils. So if I put current through these coils, what's it going to do? Create a magnetic field. Now I'm going to plug this into the wall. I have to do this for short periods or I blow fuses. Hear the arc down there? I saw the arc. You heard maybe a little hum, but nothing happened. This is alternating current. That means my magnetic fields were actually going up, down, up, down, up, down, changing, going through a cycle 60 times a second. Now on top of this, I'm going to put an aluminum ring. Aluminum ring, aluminum is not magnetic, so it doesn't respond to magnets. But it's a conductor. So if it's a conductor, it can make eddy currents. So if I put this up here, if the magnetic field goes from 0 to shooting up, what's that going to do in my ring? It's going to induce a magnetic field down. But what happens if I have north facing north? It repels and it shoots up. Now this is a little more complicated because of the AC, but we'll stop at that. So I'm going to plug it in. What do you think will happen? At least one person thinks. No one else seemed to indicate what they think will happen. And you may have thought in your head. Staying alive? Okay, so let's do this. That was really less than exciting. Not fulfilling. Well, that's why I have this. What is this, you ask? This is a whole bunch of iron rods, each one insulated so they can't make eddy currents in it. What do you know about iron in terms of magnetism? It's magnetic. It's one of our stronger magnetic materials. What happens when I put iron in a magnetic field? The domains will align with the magnetic field, making the magnetic field as much as 1,000 times stronger. So putting this in should make the magnetic field 1,000 times stronger. If the magnetic field is 1,000 times stronger, what do we suppose is going to happen? Much, much stronger magnetic field created here, hence much, much stronger magnetic field created by this, much, much stronger interaction between the two. This being science, yay! It threw it off, whereas it hardly did anything. Why? Because we have a much stronger magnetic field. Change to a brass ring. Still not magnetic. We won't ever put a magnetic thing here because it would be completely different. It's a good conductor, but it's heavier. Better conductor, but heavier. What do you suppose is going to happen? It of course depends on many aspects here. And it turns out pretty much about the same. It's heavier, but it's a better conductor, and the two worked out to be about the same. What's different about this? This is once again aluminum. What's different about it? There's a cut, so you can't have an eddy current. What's that going to do? I love science because we get to see. Now, you might think maybe I didn't stick it in, so put the ring around it. All of this is showing how those eddy currents work. Eddy currents are really fundamentally the same thing as what you're doing in a generator, except for they're working within a single piece. Let's suppose that you decide that you're going to have all the pollution for your automobile done in the creation of its batteries, and you get yourself a Prius. So you have this Prius. How many people have ever driven one? I have not, by the way.
I have a Prius.
You have a Prius. Okay. Your Prius, when you brake, it has what they call regenerative braking, right? What is it doing?
Charging.
How can you charge by braking?
Using
Obi-Wan is really good at this. Physics, yes. Is that what you said? You can generate electricity by converting your kinetic energy into current flowing in a wire. You use a generator. It's essentially the same as what we've been doing here. You have a coil and magnets. You have magnets move around that coil, and you create charge that flows, and use that to charge the battery. And so when you're doing something like driving your Prius, it regenerates, it converts energy from motion back into storing it in the battery. The energy you lose in driving that Prius is primarily lost at high speeds because you have air resistance. You can't recover the energy you lose to air resistance. So a Prius is supposed to get much more miles per charge in city driving than it does in the freeway, because in city driving you're doing a lot of starting and stopping, and you're just putting that energy back in the battery when you stop, rather than when you're driving at high speeds, putting it into the wind. Okay, sorry those two figures didn't come through. I don't know what happened. Now on to inductance. We have learned that having a current going through a coil creates a magnetic field. And we have learned that a changing magnetic flux creates an electric current. So an inductor is something that is using these principles. And the first thing we have here is something that we call a mutual inductor. Mutual because you have two coils that are interacting with each other. And so if you make a current go through the first coil, you'll make a magnetic field in the rod. And then you have the second coil. What does the second coil actually respond to? This is a really key question. It's not magnetic field alone. It is change in magnetic field. So if you just connect that battery, you will have a momentary spike on coil 2 and then nothing. Because when you connect the battery, you go from no magnetic field to a magnetic field. You have the initial spike from that change, but then if there's no change, the secondary coil has nothing. You have to have change in the magnetic field to induce something in the secondary coil. Now, how does this actually work? Well, I have some equations thrown out here. This comes from hyperphysics. The voltage in the primary coil relates to the current in the primary coil and a few other things. The voltage in the secondary likewise. It turns out that this is our important relationship. When we have the mutual inductance, the ratio of voltage in the primary coil to the voltage in the secondary coil is equal to the ratio of turns, the number of loops in the primary coil, to the number of loops in the secondary coil. Ideally, if you have no power loss in your transformer, by the way, this mutual inductor is called a transformer. Ideally, an ideal transformer, you have no power loss, and so that means VI is equal to VI, V1I1 is equal to V2I2. And so this last one is for ideal. A lot of transformers are very close to ideal, so we just work with ideal for the most part. So in an ideal transformer, the number of turns in the primary divided by the number of turns in the secondary is equal to the voltage in the primary divided by the voltage in the secondary. Notice the currents have them flipped. It's equal to the current in the secondary divided by the current in the primary. So V1I1 equals V2I2. That's where you get the right-hand side from. So this is the way a transformer works. Where do you use transformers? A couple years ago, I went with the honors, the Union Scholars, to Hong Kong. And depending on where you were, Hong Kong, China, and then Malaysia, you had either 120 or 240 volts coming out of the plugs. And so we had to get transformers so we could convert from one voltage to the other. The transformer shouldn't use energy. It's just going to, you go from 240 to 120, you cut the voltage in half and you double the current. So the total power is the same. So that's a practical place where we use transformers a lot. Here is a clicker question, I think. Yep. What is the output voltage of a transformer with 100 turns in the primary, 200 turns in the secondary, and you connect it to a 12-volt DC power supply? Yay. Okay, everybody's answered. 12, 1, 1, 3. One person got the answer right. So there are two people that, or two questions that had one, so two people that could have potentially gotten it right. Notice I underlined the 12 volts DC. What do you have to have for a transformer to work? You have to have alternating current. If it's DC, your magnetic field is constant, and thus you get nothing out of the secondary. So the correct response here was 0 volts because it was DC. That's an important thing to pay attention to. That's why I made a big deal about it. Because transformers can't work with batteries. We have the group that's making their little, I forgot what you're making, but... Yeah, coil gun. And so they're taking a couple cells, making a battery. I assume you're using one cell. And then they want to take this DC voltage and they want to get a high voltage. Well, the way to get a high voltage is with a transformer, but a transformer doesn't work with DC. So what do you guys have to have? Before the solenoid.
Capacitors. I'm naming all the parts of the system now.
The what? They have to have what's called a voltage inverter. I'm not sure why it's called an inverter, but they have a little circuit that is creating an alternating current so that they can use an alternating current with the transformer. Okay, next clicker question, and this one should be cake for you. Now we change it to an AC instead of a DC supply. Okay, everybody said the right thing. Just everybody got it in case you answered because your neighbor did instead of figuring it out. You had the relationship that V1 over V2 equals N1 over N2. So solving that for V2, and we got 24 volts. So transformers are actually a pretty simple calculation. Now a non-clicker question. Why do we use high voltage? The picture right here is supposed to be a picture. These are all pictures that came from the textbook. I'm blaming them. All three of them that didn't come out were pictures I took from the textbook. And they are in my original. What that picture is supposed to show is a power plant, and for my power plant it's just going to be like this. Well, a power plant that's producing 12 kilovolts. And then it goes through a transformer and comes out at 400 kilovolts. And then that 400 kilovolts is used to distribute the power around the country. And then it goes down to a transformer. And now that transformer, I think it was something like 3 kilovolts. And then going to your house, transformer again down to 240 volts. Something like that. I didn't memorize, I just glanced at, so I'm not sure about that voltage. What is the purpose of these transformers? Why do we have them? Why do we have 400 kilovolts crossing our country? So it is so we lose less energy in the transmission lines. The amount of energy lost in transmission lines, I've read it's 50%. I read somewhere else that it was actually really efficient. I don't know. Got to read the right sources, I guess, and now I don't know anymore. But in these transmission lines, the power lost is going to be the current squared times the resistance of the line. Now remember, we have different equations for power. We have IV, I squared R, and one more that I didn't show there, V squared over R. Why did I choose to use I squared R? I'll answer that rather than making you answer. The reason is because if I use the V squared over R, the V squared is the voltage difference from one side of the wire to the other side of the wire. Those transmission lines, hopefully that's a really small number. The current is a really large number, right? In the transmission lines, it's not the 400,000 volts because you're not grounded on the other side of the wires. So we use the one I squared R because the current, I can relate, I start with 12 kilovolts, and if I have, so many megawatt power supply, I can calculate what the current was there initially. And then through my transformer, if power is not lost, I can calculate what the new current is at 400 kilovolts. What's going to happen to the current here at 400 kilovolts compared to the current at 12 kilovolts? The current is very low because we've gone up to a very high voltage. So for the same amount of power, you have a very low current that is necessary. So you have a very low current here compared to what you're using in the house, 240 volts or 120 volts. The reason it says 240 volts in the graphic in the book is because you actually have two phases going to your house, and if you go the difference from one to the other is 240 volts. So that's why it says that. So going from 400 kilovolts to 240 volts, you have cut the voltage by a factor of, 15 or 1.5 thousand? And so the current is going to be 1.5 thousand times smaller in the transmission line, 1.5 thousand times bigger in your house than it is in the transmission line. So in your house, you're using 15 amps max for a single circuit. And so you take that 15 amps divided by 15,000, or excuse me, 1.5 thousand, and you have like 1.5 milliamps that would be going through that wire. And so the current, the power that is used by the wire is very low because you have such a low current, even though there's a lot of energy passing through it. So that's why we use the transformers to raise the voltages to high voltages. If we kept the voltages in our transmission lines going across the country at the same voltages we use in our house, we would lose virtually all of our energy in those wires. And they would get really hot and melt. So, good reasons to raise it to high voltage. Oh my goodness. I'm out of time. I will stop right here rather than starting with Joseph Henry and self-inductance. I believe in lab tomorrow we'll be dealing with inductors, and so we'll have more on self-inductance there.